Good day, I am Peter Rony. I live in Blacksburg, and let me continue after this signature slide. Who am I? Professor Emeritus of Chemical Engineering at Virginia Tech. My email address is peter@rony.com, and if you'd like to find some of my videos on YouTube, please use the search phrase Peter Rony Blacksburg. I don't do much, if any, social networking, tweetless, textless, etc. This is my favorite image about what a microcomputer is. And at the bottom you'll see some red words. I have added to the encode process some questions, information. So in fact, any computer asks lots of questions and it gets answers, and sometimes it displays the answers to the person who's using the microcomputer. On other times it uses the answers in the process of binary information to get output data. Let me focus a moment on the process block. This is the heart of a microcomputer, although without encode and decode functions, the microcomputer really would be pretty useless. So what does a process or a processor do? It takes binary information, and only binary information, changes it, processes it according to how the microprocessor is programmed, and then it outputs still binary information, but it's different from the input. It's what I call process binary information. And this goes to a decoding device which encodes that information into information that we're comfortable with. Well, I just went to Google in July 2015 and searched Google Images for microprocessor chips. And here are some of the images I turned up. These chips are really at the high end of the microprocessor chip group. And for example, you see Pentium 4, Core 17, and Core Duo, and then some AMD 64-bit chips. Well, these are the chips that are being used in the high-end computers, the servers that function at cloud computing facilities, or really fast, high-powered desktop computers. Now, I'm really not talking about these types of chips. For the simple things that I will discuss, these chips are about 1,000,000 times overkill. So I want you to just consider the simplest types, smallest microprocessors. In fact, I went to Google Images and I couldn't find any group of such simple chips, no matter how I searched. Well, I'm going to do something that may seem simple, but it has a lot of impact. How does a computer ask a question? And I'm going to answer this query by using integrated circuit chips and simple truth tables. Well, let me first give you a couple of simple 74 series integrated circuits. So the one in the lower right-hand corner is certainly not that simple. But the 7408, 7404, the 7421 and 7432 integrated circuits have been around since easily the early 1970s, so they've been around for more than 40 years. And except for the chip in the lower right, these 5 other chips are the ones that I used when I wrote my bug books 1 and 2 in 1974. Well, before I could write anything, first of all, I had to learn what are these chips and what do they do. And you will note that 4 of the chips, forget the chip in the lower right, are simple gate chips. If you want to know what a gate is, go to Google and query define gate. The 7404 is an inverter chip. And when I first started to test these chips in my office, my home in Blacksburg, my first reaction was, this is sort of toys. They don't do much, and I have no idea why there's so much interest and excitement about digital technology. But anyway, my early experiments were with these chips, and little by little I moved to more complicated integrated circuits, and once I did that, all of a sudden I became very impressed with integrated circuit technology. I won't detail that story, but today is August 2nd, 2015. I went to the website for jamco.com, and I've been dealing with them for decades, and was able to capture a list of their 74 series integrated circuits. Take a look at the 1 column, and that's how much any of these chips would cost if you would buy only 1. And that really was more or less my case. My first purchase, not from Jamco, but from a company in Missouri, was 2 chips. I would practice with 1, and if I burned it out, I would have a spare. And I rarely bought 10 chips at a time, and I never purchased 100 chips at a time. So 1 at a time is what I purchase. You can see the price per chip is really low. Look at the left column. Start at the top and go all the way down to the 74LS42N. All of those chips in quantity 1 are priced at less than $1. Well, anyway, if you're interested in specific chips, you can go to jamco.com. And here are more in the price list. Again, they're inexpensive. A couple of them cost dollars, but the other ones are under $1. So there's a whole series, and the first step I took in 1974 during the summer was to try to figure out, using my own experiments and a solderless breadboard, how each integrated circuit worked. And as I did my experiments, I had an IBM Selectric typewriter, and I created typewritten experiments that captured my learning experience with each chip. And I did this for probably a month or 2, and finally I had so many pages that I decided to create a laboratory textbook. Now, I started with experiments, and once I understood the chips, then I went back for a group of related experiments and started to write text material that would explain in general terms what the chips did. So behold my process for writing bug books 1 and 2. All right, well, when I was an undergraduate, first of all, they didn't teach me any digital concepts. My undergraduate course in electrical subjects, first quarter was resistor networks, Norton and Thevenin's theorem, boring. My next course was more interesting, transients, with resistors, capacitors, and inductors. That wasn't boring, that was pretty interesting, but it took me a while to figure out what it all meant. And I had about a 2-hour session, private session with the professor, and in those two sessions I really began to understand what transients meant, and by the final I was really good in that subject. And I liked the second quarter. Third quarter was on power, AC power, three-phase power, motors, and so forth. I joke that that third quarter was on turbo alternating Grundle flushers, whatever they were. But anyway, no digital, and that was a deficiency in my education. But I can't blame anybody, because I was an undergraduate between 1956 and 1960. And who could anticipate how important digital electronics and microprocessors would become? But anyway, starting upon my graduation in 1960 and continuing until my employment at Virginia Tech in 1974, I was completely ignorant about what digital technology was all about. Well, this is an image for electrical engineers. I'm not one. I'm a chemical engineer, and here is something that is closer to what I should do. Here are breweries with tanks and valves and pipes and temperature measurement devices and all that. This is cool. I like this stuff. I liked this stuff until I got off on a tangent called microprocessors. But in principle, this should be me. Well, if you look at those brewery systems, you have mechanical valves. Went to Google Images, and here are a group of them. You more likely have pneumatic valves, which are automatic valves. You don't need to change the valve position from off to on or on to off manually. You can send an electrical signal, and the little thingy-majig above the valve will turn the valve. So these valves, they're expensive, but they help you automate a brewery plant. All right, let me skip the complexity. Here's an image of a single tank. Remember it. Oh, but look at the green level. That's the level of the liquid within the tank. And in many cases, one objective is to keep that level at a constant. If it's too high, the tank will overflow. You'll have a mess on the floor. And if the level is too low, then your process will fail. And couple that with a pneumatic valve. So in the images that I will show you a simple schematic diagram of a tank and one or more valves. Also simple diagrams. So here is such a schematic diagram. This thing on top is a tank, and the two items SO and S1, or A and B, are the pneumatic valves. Well, if you take a look, you can make the obvious conclusion. If valve A or valve B is closed, no liquid will flow. For liquid to flow, A and B must be open or on. So here is what what I call a truth table with words. The inputs are to the system are valve A and valve B. The water flow is the single output, and the question is, will there be any flow from this tank with two serial valves? The answer is only if both valves are open. If both are closed, or if either one is closed, no liquid will flow. Well, let me get back to a topic that I treated a couple of videos ago. We can encode the valve and we can encode the flow. We'll assign a logic 0 if a valve is closed and a logic 1 if a valve is open. That seems simple and reasonable. And at the bottom of the tank and after the valves, if there's no flow, we will assign a logic 0, and if there's flow, we'll assign a logic 1. So we have two different 1-bit encoding tables, and they're pretty simple. Now, here's the question that we will ask of the system. Can water flow? Using our 1-bit encoding tables, we can now create what is called a truth table. And here's a classic truth table on the left. Now, what distinguishes the truth table is they're only binary symbols, either 0 or 1, to the left of the vertical bar and to the right. There are no words, so this is the unique aspect of the concept, the jargon truth table. Well, I would like to look at the truth table in a different way. I call it a question process. And the question is, are both inputs at logic 1? From the previous slide, that question is comparable to, are both valves open? And as you can see from this truth table, yes, there is liquid flow if both inputs are logic 1. Well, how do we ask this question? We can ask it very simply. We don't need Intel Core Duo microprocessor chip. We don't even need a microprocessor. We can go back to early 1970s technology and use a simple integrated circuit whose pin diagram I show you, and there are 4 2-input AND gates, which means you can ask 4 separate questions using this chip. This chip probably costs, say, 40 cents or less, so you can ask a question for 10 cents. And that's it. So this 7408 chip, I call it's a processor chip. Why? Because it asks a question and gives an answer. Well, let's have a slightly different situation. Rather than 2 valves in series, let's separate the valves and now put them in parallel. And you intuitively understand that if either valve A is open or valve B is open, or both A and B are open, then liquid will flow. It's different. So, we have a different truth table. And take a look at the inputs and outputs. If both valves are closed, then we have an output of logic 0, which means no water will flow. But if either or both valves B and A, then we'll have flow. So how do you ask this question? You pay 30 cents and you purchase a 7432 input OR integrated circuit. which has 4 2-input OR gates. So this is dirt cheap. And all you need to do to ask the question is this specific integrated circuit. Now, what if we have 3 valves in series? In this case, you understand that all 3 valves must be open if liquid is to flow from the tank. Well, let me give you another chip. This is the 7421 dual 4-input AND. Now, we don't need all 4 inputs. So you can see the numeral 1. That means I apply logic 1 to pins 5 and 9, leaving the remaining pins for sensing the condition of 3 valves. Here's the truth table. Sort of interesting, very simple. Only if C, B, and A each are 1, then can Q, the liquid flow, actually flow. All other conditions, there is no flow. Well, how about 4 valves in series? Well, I can sell you a different chip, probably for 40 cents, and it has 2 4-input AND gates, which means you can ask 2 different questions, 2 different systems, and it'll cost you 20 cents a question. Well, now let's push the envelope and have a tank with 8 valves in series. Let's see, SO 1, 2, 3, 4, 5, 6. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. The bottom valve is listed as S4. That should be S7. So this is the truth table, which I created today, August 2nd, for these 8 valves. And look at just a sampling of the whole table. It goes on and on. It's very high vertically. So after a while, I just pooped out and I substitute the remaining rows with the statement, missing rows to save space. But the bottom line is the bottom row. If all valves are 1, then the flow Q is logic 1, which means that a liquid will flow through this series of valves. Now, what I showed you, this vertical column, is overdoing it. Really, the only important decision is what is the condition, the single condition, when water can flow. And that condition is when all 8 valves are open, which means that all 8 valves are at logic 1, and only then can water flow. For any other combination, water cannot flow, so there's a logic 0. And I won't continue. I think you get the idea. So you should be able to write a truth table for a 3-input OR gate, a 4-input OR gate, and a 5-input OR gate. And in each of these situations, if any one of the valves is open, then liquid will flow. And here's another situation. The unique situations for the valves is all 8 of them are closed. That means in the truth table you have 0, 0, 0, 0, 0, 0, 0, 0. And then no liquid will flow. So for the Q column in the truth table, the value uniquely will be 0. Now, any other condition for these valves and water will flow through at least 1 or maybe more valves. So this is an 8-input OR situation. Now, you can have combinations of series and parallel, and that's what we have here. In general, you wouldn't have this situation in industry. Why would you need 3 valves in series or 2 valves in series? But in electronics and digital electronics, there is a special chip called an AND or invert gate chip, and electronic systems, this is a pretty useful chip when you're creating computer systems. Well, I think you get the idea that you can ask a question and get an answer with a 10 or 20 cent circuit on a chip. You don't need a microprocessor chip, not even the simplest one. But basically, what I'm telling you is one of the things that occurs in the process function is to ask a question and output an answer. And with microcomputer systems, when you have a degree of complexity and a microprocessor chip, such a chip could ask perhaps 100 questions and do it in less than a second. And that indicates how versatile and powerful microprocessors are. Thank you for viewing this video.